Alright, we're going to look at confidence intervals now in this chapter. So basically the idea of a confidence interval is that you take a sample and then you infer something about the population. So that's all we're doing here. And basically when we do a confidence interval, we're talking about what's going to happen if we did this method many times. I'm not going to go through this activity here. Remember we had a term called a point estimate. So a point estimate is a statistic that provides an estimate of a population parameter. So we can use x bar to estimate mu, or we can use p hat to estimate p. So it's just one value. It's the best guess at the unknown parameter. Back in the other chapter, ideally we're trying to get a point estimator that has no bias and low variability. I'm going to skip over this here. Alright, when we did a confidence interval, all we were doing is we were taking that point estimate plus or minus the margin of error. The margin of error just tells us how close the estimate tends to be to the unknown parameter in repeated sampling. The confidence level is the overall success rate for the method of calculating the confidence interval. So if you remember, we looked at, we did a problem with M&Ms. And we looked at, everybody in the class created like an interval, and we looked at how many of those intervals actually captured the true proportion. So that's just what the confidence level means. Usually we use 90% or higher. We use 90, 95, 99 are the most common used ones. We can't ever be 100% confident because you'd have to have a very large interval. So again, remember what's happening here is you have a population. If we took many samples and we calculated many confidence intervals, if we were doing a 95% confidence, 95% of those intervals would capture the mean. So that's all that this is kind of illustrating here. So here's one that doesn't. When you do this in real life, obviously you take one sample and you make your interval from just that one sample. But the idea of being X% confident is that when you repeat this many times, X percentage of the times, you're likely to create an interval that captures the true value that you're looking for. Alright, make sure that you can distinguish between these two things here. Sometimes they do ask you that on an AP question, and you just want to make sure you do both and not just one or the other. So interpreting a confidence level and a confidence interval. If you're interpreting the level, so you're actually interpreting the numbers, then you're saying that you're 95% confident. When you're interpreting the interval, you would say we are 95% confident the interval from blank to blank captures the actual value of the true proportion of yellow M&Ms or something like that. If you're just interpreting the level, that is a more generic one. The interval has to be in context of the problem. The level is just, what does it mean to be 95% confident? So you could just say that, if you repeated this process many times with many samples and created many intervals, 95% of those intervals should capture the true mean. It never tells us the chance that a particular confidence interval captures the population parameter. It just gives us a plausible set of values. Alright, the general formula, instead of saying margin of error, it's going to be the statistic. So the estimate and the statistic, it's the same thing here. So it's x bar and p hat plus or minus a critical value times the standard deviation of the statistic. Alright, so again, the margin of error is the piece after the plus or minus. You decide the confidence level, or the problem does. The critical value is going to be dependent on the confidence level. If you want to be more confident, you require a larger critical value. The standard deviation is depending on the sample size. The margin of error, so the intervals are going to be smaller if your confidence level decreases, or they're going to get smaller if your sample size increases. We had conditions that we checked for each one. So we always check the random condition. So either the data is from a random sample or it can be from a random experiment. The normal condition, so if it was means, if you're doing inference on means, the sampling distribution is normal if the population is normal, so you had to check to see if the population was normal, or you checked if the sample size was large, so greater than or equal to 30, because of that central limit theorem. We also had situations in which, when we were using the t-distribution, that we did a graph, and we would just check, does the graph look normal? So there might be times where you have to check the graph. For proportions, the only thing you need to remember is that NP and n times 1 minus p. In the case of confidence intervals, you're going to use the p hat because you don't know what p is. And then lastly, we had that independent check, which is the same for everything. So either the observations are independent if you're sampling without replacement, or your sample should be less than 10% of your population. Alright, so that was just the kind of the basic ideas here. Let me look at the one for, let's just go in deeper a little bit with proportions. Let's see here. Let me get, this is an example. When you're doing a confidence interval for the proportions, we're going to check that normal condition. Remember the mean, and this is the standard deviation formula that we're going to use, but we don't know what p is, so like that p and the p here, we're going to replace it with p hat because we don't know what it is. Alright, this goes back to your general formula. So here, your standard deviation is this formula. Like I said, we're going to replace the p with p hat. When you replace the p with p hat, you call it the standard error. It's just, that's all it is. It's just when you replace the statistic for the population parameter, you just call it the standard error. You can find your critical value using the z distribution, so we could use inverse norm. And they're going to show you here how to use the table. Alright, so this is the formula. It was p hat, so that's the statistic, plus or minus the critical value, so that z star, times the standard deviation of the statistic. So that's the formula there. This is true as long as you had to check that n times p hat is greater than or equal to 10, n times 1 minus p hat is greater than or equal to 10. You also have to check the random condition and the normal condition, the independent condition. Alright, so this saying here, if you wanted to create the 90% confidence interval for a proportion of red beads in a container. So that's the sample proportion. The conditions were already checked, so they checked them back here. So it was a random sample. Both of those conditions, see how they plugged in p hat instead of p? And they sampled without replacement, so they checked the 10% condition. So those conditions were met. So they're going to construct their confidence interval. For a 90% confidence level, you're going to use that. We always did, I would draw a picture, 90% was in the middle, so you had 0.05 in each tail. We would do inverse norm 0.05 or inverse norm 0.95, and that's the number you'd get. And then you could plug everything into that formula. So there's the p hat, so that's what they got from the sample. There's their critical value. There's their p hat again, 1 minus their p hat. And there's their sample size. And then they created the interval. So there's their interval. Then they can do their interpretation. So we are 90% confident that the interval from blank to blank captures the actual proportion of red beads in the container. And then they're just giving, you know, now they're going back to what the teacher had claimed. And since 0.5 is not contained in the interval, they can say that they doubt the teacher. Alright, when we did this confidence interval, I introduced these 4 steps to you, and this is where you need to start using them. So on the AP test, if you're asked to calculate a confidence interval, you need to follow the 4 steps. I don't care if it doesn't say that, you just need to do that. So the first step, what parameter do you want to estimate at what confidence level? Plan, identify the appropriate method. So you need to state what method you're using. You want to check your conditions. If the conditions are met, then you're going to perform your calculations. Conclusion, interpret your interval in context of the problem. All right, we also talked about how we could find the minimum sample size. So if we were going to start before we actually, so we were going to go out and collect our data. We don't have the data already collected to create the confidence interval. We're going to go out and collect it. So what we did is we took the margin of error formula and you can solve it for n. And that was one thing I showed you how to do. You'd also just leave it like this and plug everything in and then solve it for n later. So the problem with this formula is that you need to have some prior information about p hat. So sometimes we would use a guess. So if there was like a prior study that was conducted or something like that, we might use a information from that prior study to actually like figure things out. Sometimes if we didn't have any prior information, we would use p hat because the margin of error is the largest when p hat is equal to 0.5. And this is just the minimum sample size. So if you wanted to figure out the minimum sample size needed to estimate p within, and this is from an earlier problem, 0.03 with 95% confidence. So 95% confidence is 1.96. They want a margin of error of 0.03, so that's what they're plugging that in there. They don't have any prior information about p hat. So right now they're just solving everything for n. And then they're going to substitute 0.5 in because they don't have any prior information. So the minimum sample size, we're going to round it up to 1068. And that'll ensure the margin of error is no more than 3.03 at a 95% confidence level. And you can read through the summary here if you would like.